Okay, we're live. Let's share screen. Let me know when you guys can see that.
Got it.
Got it.
Okay, so we have spent now the past several weeks building up to what's really going to be flight planning. We've learned aircraft systems, instrumentation systems, different ways to define airspeed and altitude, a lot of aerodynamics, and basic flight maneuvering. And tonight's going to be aircraft performance planning. And once we get through this and some discussions on weather theory and stuff like that, we'll be ready to talk about how to do flight planning. So hopefully you guys kind of feel the buildup of information to the point where once we culminate to the final 3 or 4 classes, you'll be super comfortable planning a cross-country flight given all the information you've learned. With that, aircraft performance planning, we're going to look at all phases of flight and what you'll be expected to know from a flight planning perspective. And we've looked at a few performance charts throughout the classes. I know I've pulled up the operating handbook for the Piper Arrow a couple times, but we're gonna deep dive each and every type of performance chart that you might see. Not only the ones you'll see on the test, but even ones that you might find in an aircraft that you fly someday. So before we get into the actual planning portion, I've got like 2 or 3 slides as review to go over like some of the atmospheric things that we've already talked about, which will be key to the performance discussion. But before we do that, there is a Federal Aviation Regulation, 14 CFR 91.103, that is the backbone or outlines what a pilot is required to do during his pre-flight planning. Now, there's a couple things you'll notice when you read through this. Number one, it's limited, right? It doesn't say that the pilot needs to basically understand everything for the specific flight that they're carrying out. So they do spell out exactly what the pilot needs to do. And the second thing that you might notice is there's probably things missing from this list, which is, I guess that's the federal government for you, kind of. You'll use this in your training. You will have to recite this for your flight examiner. But when you start doing flight planning, you'll kind of have your own way of doing it. No doubt you'll cover all these areas, but there's definitely things on this list that I go through when I plan a flight, and we'll learn more about that when we do our flight planning sessions. But for a flight, IFR, or not in the vicinity of an airport, which means basically you're taking off from an airport and leaving, going somewhere else, you need to become familiar with weather reports, forecasts, fuel requirements, which is, we're going to talk a little bit about that tonight. Alternate airports, so alternatives available if the planned flight cannot be completed, and any known traffic delays advised by air traffic control. It goes on to basically mention that the pilot has to become familiar with runway lengths and takeoff and landing distance. We're going to learn in a little bit why that's important. And then finally, it goes on to talk a little bit about helicopter requirements over and above fixed wing requirements. But then it also states that for civil aircraft other than those specified in B1, you have to become familiar with aircraft performance, airport elevation, runway slope, aircraft gross weight, wind, and temperature. So it definitely is a extensive list of items that you have to become familiar with. But there are a couple other things that I think when we go through some of the future classes on flight planning, you'll appreciate that are maybe not in this list. So I wanted to show you guys that. It will come up again when we talk about flight planning, but there are some elements in this series of paragraphs that we're going to talk about tonight. All right, let's review a little bit on pressure, temperature, and pressure. When we discussed aircraft instrumentation, the pitot-static system. If you guys remember the pitot-static, it's your airspeed indicator, your altimeter, your vertical speed indicator, all work off the premise of static pressure, and also are highly susceptible to errors caused by pressure and temperature differences because it's a pressure static system. We're going to reference some of those principles here tonight because, as you might imagine, the performance of an aircraft is highly impacted by air pressures and air temperatures. And when you consider at the altitudes that you'll be flying at, and I put it up here on the screen in the chart, you're going to be flying through areas of high pressure, areas of low pressure. And if you've got a standard atmosphere, of course, your temperature drops pretty drastically as you increase in altitude. So all those elements affect the way that the aircraft will perform. And it also affects the aircraft manufacturer when they go to test their aircraft and put together their operating handbook. They are cognizant of the differences in pressures and temperatures with altitude. So they cater the performance charts for the pilot so that they can plan the flight successfully. And of course, there's that equation. As just a quick refresher, PV equals rho RT, P pressure, V volume, rho air density or fluid density. R is a constant depending on what fluid is being discussed, and T is temperature. So the important thing to remember, pressure and temperature related directly. If you're discussing a fixed volume of air whose density does not change, as pressure goes up, temperature goes up, vice versa. Pressure goes down, temperature goes down. And you can see that on the chart here. As pressure is going, as altitude is increasing, air pressure is going down, temperature is going down. Now, and I maybe didn't do a very good job explaining it in the prior session, but one of you guys want to take a stab at why the air pressure goes down as you increase in altitude?
Because the air becomes less dense.
I bet that is a reason and a byproduct.
So are we talking about the relationship between pressure and temperature? Is that question meant to reinforce that? Because the temperature goes down, therefore the pressure goes down, or?
No, it's what I want to do is explain the reason why as you go up in altitude, pressure decreases.
Oh, I always thought it was because the air particles become farther apart.
Yeah, and when I think about it, I mean, let me explain the way I was explained, the way I learned it, and then maybe your explanation is correct. So if you think about a column of air, like think about a square inch column of air starting at the ground and going all the way up to, say, 80,000 feet. If you were to take that column of air and weigh it, it would weigh about 14.7 pounds. And so if you look at standard atmosphere values, the standard atmosphere pressure value at sea level is about 14.7 pounds per square inch. The reason it's 14.7 pounds at the surface is because all the air above it in that column is weighing down on it.
Yeah, it's like water.
Mm-hmm. Exactly. Yep. As you go up in altitude, there's less air above you to produce less force at that particular altitude.
Yeah, so what I was explaining were the symptoms of what was happening.
Right, exactly. And therefore, yes, there's less pressure, so the density goes down. That's correct. Yep. Okay. I'm going to clear a couple definitions here, which are going to be critical to understanding performance calculations. Standard lapse rate, you guys heard that definition when I posted that Slack question. There's a couple different lapse rates that you can use. There's a dry lapse rate. There's a wet lapse rate. There's in-between lapse rates. When it comes to aircraft performance planning, we use what's called the standard lapse rate. And what that is an assumption that pressure decreases 1 inch of mercury per 1,000 foot, and that temperature decreases 2 degrees centigrade per 1,000 feet, up to 36,000 feet. When we start talking about weather theory, we'll introduce a couple different lapse rates. But for now, performance planning for your aircraft is an assumed standard lapse rate. When we do the calculations, we'll utilize some of these assumptions.
And those deltas are based upon the starting position of the plane, right? So
that's correct. Mm-hmm.
So if your pressure, let's say your pressure is not on that chart because you're somewhere and it's just different for whatever reason, you would start that as your base number. And then as you go per 1,000 feet from there, you would add 1 inch based upon that initial number, not just 29.92 at 0, 28.86 at 1,000 feet, right?
That's right. That's correct. That's absolutely correct. You have to start at the reference altitude that you're at.
Okay, cool.
Mm-hmm. Yep. And furthermore, when we talk about aircraft performance planning, all performance planning by the manufacturer is performed in a standard atmosphere. We've talked about that before. It's an altimeter setting or a barometer setting of 29 or 0.902 inches mercury and 15 degrees Celsius at sea level. So just to kind of piggyback, Alan, on what you said, if the aircraft manufacturer is testing their aircraft at 5,000 feet, then they're going to test it in an environment where the pressure is 24.89 and 5.1 degrees Celsius.
Got it.
Yep. And also, I did fail to mention this when we talked about instrumentation, but I kind of wanted to wait until we got to this point in the schooling. But above 18,000 feet, or what's known as flight level FL 180, standard atmosphere is used within your altimeter to assign all altitudes. Now, the three of us, unless we go off and be jet pilots someday, we're probably not going to encounter this, but should you have to fly above 18,000 feet, you reset your altimeter to 29 or 9 or 2. All aircraft are then on the same, what's called a reference plane, a standard datum plane. All right. And then we did talk briefly about density altitude when we reviewed types of altitude. If you remember, absolute altitude, mean sea level altitude, above ground altitude, and density altitude. And we'll just review it real quick here. But density altitude, by definition, is the pressure altitude corrected for non-standard temperature. And of course, we also discussed a little bit about how air density highly impacts aircraft systems, such as the air intake on your engine, the efficiency of your propeller, and the ability of your airfoils to produce lift. These three by far are highly impacted by air density. To the point where you would definitely notice a difference even as early as 4,000 feet. Okay, so what I'm going to do, I want to skip over here really quick. Let's look at this chart one more time. So again, important to note that in a standard atmosphere, where your sea level pressure is 2992 and your sea level temperature is 15 degrees Celsius, if there's an assumed standard atmosphere throughout the whole altitude envelope, then each altitude can be defined as pressure altitude. Now, this is an ideal state. You very rarely have this, obviously. But when we define the term pressure altitude, it is this table exactly. It's a 2992 pressure at sea level and a 15 degrees Celsius at sea level. And then each altitude has these specific temperature and pressures. So if someone were to ask you, what is the standard temperature at a pressure altitude of 6,000 feet, your answer would be 3.1 degrees Celsius. And likewise for the pressure. So this is important to note because density altitude takes a departure from pressure altitude based on temperature. The density altitude is the pressure altitude for that particular level, but corrected for temperature. So for instance, if you're at 6,000 feet and the temperature is above 3.1 degrees, let's say it's really at 10 degrees, then your density altitude will have a different value than your pressure altitude. And the reason is, all things constant, if temperature changes at a certain pressure altitude, your density is going to change. Make sense?
Yep.
Yes.
Okay. Okay, so therefore, your density altitude is the vertical distance or the altitude above sea level in a standard atmosphere at which you can find an air density. So that's just a fancy way of saying every time you change altitudes, you'll have a different air density. Oh, by the way, if your temperature is not standard for that altitude, the 3.1 degrees in the previous example, then your density altitude will be different than your pressure altitude. So example, I'm up in the mountains at 6,000 feet. And I think I've got, actually, I think I've caught myself a mistake. I think that should be 3.1 degrees. We just reviewed that, didn't we? I'm up in the mountains at 6,000 feet and my temperature is 3.1 degrees. My density altitude is 6,000 feet. We just kind of went through that one. If I'm in Texas, well, not really even Texas. If I'm down at 3,000 feet and my temperature is 35 degrees Celsius, my density altitude is still 6,000 feet. And the reason for that is, if I go back to my chart, remembering the value 35 degrees Celsius, if I go back to my chart, the standard temperature at 3,000 feet is really 9.1. And if you were to do a density altitude calculation, you would find that although you're at 3,000 feet, your aircraft is going to perform as though it was at 6,000 feet. Because of your temperature difference. Does that make clear sense to you guys?
Yeah, it sure does.
Yep. Chris?
Yes.
Okay. So what you're going to find is, although in this particular session we talked a lot of ideal states like standard atmosphere and standard pressure altitudes, it's never the case. You'll always be making adjustments for temperature, and you'll always be taking into consideration density altitude for most of your performance calculations. So let's just run through a quick example because this is an important one. You'll see it on the written test, and quite frankly, when you're doing performance planning, you'll always be calculating density altitude, especially if you're leaving Texas and going to like New Mexico or something like that. So I've got a couple assumptions here. My altimeter setting or my barometric pressures 2.9 or 2.5 inches mercury. My outside air temperature, 81 degrees Fahrenheit, and the airport that I'm currently at is 5,250 feet mean sea level, so above sea level. And so we want to find the density altitude. In the end, we want to determine the density altitude from these conditions. And we're going to use what is called the density altitude conversion chart here. Now, what we defined pressure, or I'm sorry, we defined density altitude before. What was the definition of density altitude?
The altitude, I can't remember how you worded it. I know what it is.
It was very eloquent, I know. It's the pressure altitude corrected for non-standard temperature.
Yeah, I kept wanting to say the actual versus the calculated.
Mm-hmm. Yep. So it's your pressure altitude corrected for non-standard temperature. And so right off the bat, if we want to find density altitude, we have to know what our pressure altitude is.
Yep.
Okay. Now, the first thing you're thinking, because it was definitely kind of the way that I was thinking, you already told us what our altitude is. It's 5250, right? But that's not right, because that is the altitude that you're at with this altimeter setting, 29 or 25, right? What is the altimeter setting? Can you guys tell me what the altimeter setting is in a standard atmosphere?
At mean sea level?
At 0 feet mean sea level.
29 or 9 or 2?
You got it. So in order to find my pressure altitude, I've got to do one of two things. If I'm in my airplane, I'll set my altimeter to 2992, the standard reference datum plane for standard atmosphere, and I'll read what the altimeter is telling me, or I can do a calculation. I can do a math problem. Either way, in order to find density altitude, I've got to have pressure altitude. Why? Because density altitude is pressure altitude corrected for temperature. Hello. So how am I going to do my math? Well, remember we mentioned here that pressure decreases 1 inch mercury per 1,000 feet. So that's in a standard atmosphere, that's how we're going to perform our math. So I take the difference in my pressures. I've got my standard pressure here in a standard datum plane, subtract my actual pressure, and I've got 0.67. I take my 0.67 and I multiply it by 1,000, because there's 1,000 feet per inch of mercury. And I come up with a 670-foot altitude difference between my current elevation and pressure altitude. Make sense so far?
Mm-hmm.
Yep.
Okay. So therefore, my pressure altitude is my current altitude plus the difference. And you know whether to add or subtract that 670 based on whether your current altimeter setting is below or above standard. Now bear with me through this explanation. If your current altimeter setting is below standard, that means that you're actually higher than your standard datum plane. Why? Because as you go up, your pressure goes down. So if you've got a lower altimeter setting than your standard datum plane of 29 or 9 or 2, it means your pressure altitude is higher. So you must add that difference to your current field altitude. Understand or complete confusion?
You gotta get it.
Good. Chris?
Yeah.
Okay. You guys aren't lying to me, right?
No.
Okay. So just really quick, density altitude, you find pressure altitude first, and then you adjust for your temperature. So we just took a standard datum plane of 29 or 9 or 2, found the difference between our current airport elevation and pressure altitude, and have determined that pressure altitude is 5920. So knowing this, we can come down here and utilize this nifty chart, which you'll become familiar with as you study for the written test. We'll find our pressure altitude of 5920. Let's just call it 6,000 feet. And our actual temperature of, I think it was 81, right? Yeah, 81 degrees. And come up with an approximate density altitude of about 7,000 feet. Oh, oops, I screwed that up, guys. Sorry. 6,000 over here. 8,000 feet. Good stuff. Does that all make pretty good sense?
Yep.
The outside
Okay.
air temperature is not modified. That's just straight outside air temperature, right?
Exactly. Outside air temperature is what you would read on a thermometer right there at the airport.
Got it.
Mm-hmm. So you can either, depending on how comfortable you are with the math, you can either do the math problem here to find your pressure altitude, because you know that every 1,000 feet pressure drops by 1 inch of mercury, or you can utilize this table over here as what they call a pressure altitude conversion factor. So you find your altimeter setting, 29 or 25, so like right here somewhere, and you've got an addition as opposed to a subtraction, an addition of 673 or whatever we came up with, 670. So you can do the tabular method or you can do the math problem method. All good?
Yeah.
Okay. All right, so that's density altitude. Now, of course, there's flight computers and there's online tools for flight, you name it. But again, you're going to want to know how to do the math, the tabular method. You're going to want to be able to do it this way for the written test and for the flight test. So important stuff. All right. So now that we've talked density, altitude, and how to find it, we're going to start discussing different phases of flight. We're going to start with takeoff, where density altitude has its highest probability of affecting your flight is right at takeoff. And beyond density altitude, which we're going to get into in a minute, a couple other factors that pilots sometimes don't think about until they're faced with the situation is that runway gradient and the condition of the runway or the type of surface that it is actually affects your aircraft takeoff performance very significantly, to the point where you will make, I'll say, non-traditional decisions based on what your surface is or what your gradient is. For example, we usually take off and land into the wind with a headwind. Well, if your runway gradient is not favorable, as in if it's uphill, then you would likely take off downhill, even if it meant taking off with a tailwind. So all things to consider as you're flying into strange airports and gravel runways, grass runways, that kind of stuff. And from a performance standpoint, of course, you'll typically be planning your flights into paved runways. So we'll go over a couple of the considerations that you want to keep in mind when you're doing your planning. The most important consideration is the takeoff distance. And it's applied in the CFRs that we read, the 14 CFR 91-103. It's important because takeoff happens to be the most dangerous, statistically dangerous part of flight. And all it takes is a simple math error or chart reading error to end up off the end of the runway. So minimum takeoff distance is a number you will always become familiar with for the aircraft that you fly. The wind direction is the, I'll say, next important consideration. Let's hear what you guys think. Do you know why the airplane it preferably wants to take off into the wind rather than with or with a tailwind?
It reduces the amount of power you have to take off, because you're getting better effects on the wings.
Yeah, that's exactly right. And to add one more item, or to add another definition, it will decrease your ground speed but increase your true airspeed. If you guys remember, true airspeed is defined by the aircraft's actual speed through the relative air mass. So, Alan, to your point, you've got a headwind of, call it 20 knots. Even if the airplane is standing still, if there's a headwind of 20 knots, then it thinks that it's going at an airspeed of 20 knots. The airplane does. So consequently, for this A320 at 130 knots airspeed, it's only doing 110 knots over the ground. So it's going to cover less distance to take off than it would in a zero wind condition. So yes, right on. With a headwind, the aircraft sees a faster true airspeed, which allows it to take off in a shorter distance. You'll notice this if you guys fly commercially. You'll get in the airplane, you'll pull up your aviation weather app, and you'll see you've got a stiff headwind. And the first thing you'll say to yourself is, all right, this guy's going to take off in like 2,000 feet, and it'll be very noticeable. Gross weight is the next important factor to your takeoff calculations, takeoff distance calculations, and you won't necessarily, depending on what kind of aircraft you fly and what your operating handbook looks like, you won't always have a performance chart that takes into account weight. Some of the aircraft, like we mentioned, I think during the weight and balance session, some of the aircraft have handbooks that are published with only max gross weight considerations, and then it's up to the pilot to determine that, that's the maximum operating limit for the aircraft. Some have charts that do take into account different weights, and we're going to look at that in a second. But just from a theoretical perspective, when your weight is higher or at max gross weight, Newton's second law comes into play, right? You've got a greater mass to accelerate, so it'll take a greater force to get it to the right airspeed. Or if you're using max force, if you're using the maximum force your aircraft can output, which is, typically how we take off in an airplane, then your acceleration will be affected. The higher your weight, the higher your liftoff speed required. And if you guys remember back to the aerodynamics session, when you're heavier, your aircraft requires a higher angle of attack to maintain the same airspeed. So weight requires a higher true airspeed to actually take off. And then probably the least of concern is increased rolling drag. This is just the fact that your tires are made of rubber, and the heavier your airplane is, the greater rolling friction there is between the tire and the runway surface. And then, of course, there's density altitude, and we kind of already touched on this. As your air becomes less dense, your propeller is less efficient, your engine is less efficient, it takes in less air, and your wings do not lift as efficiently as they would in thicker air. Now, I want to spend just 2 seconds talking about this right here. This is a very important point down here. The FAA handbooks spend probably 2 or 3 paragraphs discussing this point down here. I want to touch on it because it does come up in the written test, and it's something that I truly I can't really remember, but I feel like I didn't understand this that well when I first took my flight training. What the book's going to tell you, and what you'll find when you start your flight training, is that you can take off from a Texas runway at 700 feet, and your aircraft will lift off at, I'm just going to make up a number, 70 knots indicated airspeed. And then you fly your airplane to, you know, Colorado Springs, where the elevation is 6,000 feet. And when you take off from Colorado Springs, where there's high density altitude, your aircraft is still going to lift off at 70 knots. And the first thought that you've got is, well, that's doesn't make sense, right? Because, you know, Adam just told me that because of density altitude, it takes a lot longer to get down the runway. The engine doesn't generate as much power, and the wings don't work as well. So it's gotta take off like at a higher airspeed for the wings to work properly, right? Like 80 knots or 90 knots. But here's what you got to keep in mind. And I'm gonna just make a little drawing here. I hope it's not too ugly. Here's the airplane. And on the airplane's wing, you've got your pitot tube. If you guys remember, your pitot tube controlled which instrument?
I've forgotten.
That's the one with dynamic pressure. It's airspeed.
That's it. Yep. Airspeed, indicated airspeed. So when you're at high altitude in high density altitude conditions, your first thought is, well, because of the high density altitude, it's definitely going to take a higher airspeed for me to take off, higher indicated airspeed. And what I'm going to tell you is, no, it's the same, and here's why. Because your wings, based on Bernoulli's principle, which Chris and I just reviewed this week, require a certain amount of pressure to lift the aircraft off the ground. If you remember, you've got an area of high pressure below the wing and an area of low pressure above, right? And the pressure required to lift the aircraft off the ground does not change. That same pressure is entering the pitot tube. So your pressure entering the pitot tube and your pressure here, your high pressure, we're just going to call that dynamic pressure as well, are always going to be the same. The pressure to lift the aircraft off the ground is always going to be the same regardless of altitude. And the pressure going into the pitot tube will always be the same. So your indicated airspeed will be the same regardless of what elevation airport you take off from, regardless of what density altitude you're operating in.
That actually makes sense.
Yep. Now,
Your actual airspeed.
Yeah. Now, what I'll tell you is, the three of us, we're not totally dumb, because the true airspeed does increase. It actually does take a faster speed through the air to obtain the correct dynamic pressure to lift the aircraft off the ground. Why? Because the air is not as dense.
So what's nice about that system is it allows you to get consistent with your takeoff speeds.
Yep.
Your indicated airspeed for takeoff, because you're not having to remember 15 different numbers for at which speed you lift. That's kind of nice in that respect.
Oh yeah, no, it's great. I mean, if you think about it, and I don't have, I probably should have been prepared with some numbers, but yeah, if you're operating from an 8,000 foot runway, your true airspeed, if your true airspeed at sea level for takeoff is 70 knots, it's easily going to be about 100 knots at that 8,000 foot runway. It's drastic. So yeah, to your point, the fact that you don't have to memorize different values on your gauge, you can just shoot for the same value all the time is excellent. Yeah, it makes it really easy to know when you can take off. Okay, so just real quick, takeoff performance, you're looking for your biggest parameter is minimum takeoff distance. That's the most important. And your considerations are the wind direction, the weight of your aircraft, and the density altitude for which you are operating at, which we just learned a minute ago how to calculate. Okay, and here is a sample takeoff chart. This chart happens to be from the reading material, and it's one of the more complex types. It actually does take into account the weight of the aircraft. And let's just walk through real quick how to operate on this thing. I'll just do the example that's in the chart. So I've got a 15 degrees Celsius day, which is standard. I've got my pressure altitude of 5650. So someone's already calculated my pressure altitude. There's the weight of my aircraft, the headwind component at the airport, and a couple other assumptions here: full throttle, mixture lean, flaps up, landing gear, cow flaps. So essentially, I've got all my ambient conditions, all my atmospheric conditions. They've already done the pressure altitude calculation for me, so that's easy. And so here we go. These kind of charts you always enter on the left-hand side of the chart and make your way across the different parameters. So let's just go through this one. So I'm going to enter at my 15 degrees Celsius outside air temperature, and I'm going to follow the chart all the way up to my almost 6,000 foot pressure altitude. See, here's 50, what do we got? 5650. So 5650 somewhere in here. And at that point, we escape over to the next parameter. We follow the dotted line over to the next parameter, which is weight. And what are we doing with weight? 2950. So my 2950 line is, it happens to be what appears to be maximum. So we don't have to follow any of these contours in this example. If the weight was like 2,600 pounds, then we would draw a line at 2,600, take our point here, and follow it down the contours until I get to my 2,600 point, at which point I would escape out to the right to the next parameter. But this one is operating at max gross weight right here. So we're just going to escape to the right away. No contours. Then I get to my wind component, which is 9 knots headwind, which is right here. So they followed the contour down and escape to the right over to our next parameter, which is the answer to our question: what is our minimum takeoff distance? And so some of the questions are going to tell you that you've got an obstacle, 50-foot obstacle. Some say that you won't. But I guess in this case, they decide to do both examples. So if you have no obstacle, then your takeoff distance over here to the right is, what do we got, 1,300 feet, 1,400 feet. And if you've got an obstacle of 50 feet, you follow the contour up to the termination point here, which is 2,300 feet. There's your answers right there. So that is what I would call the involved performance chart for takeoff distance. Is that example clear for you guys?
Yeah, that's a pretty helpful tool.
Okay. The aircraft I fly happens to not be or have that complex of a takeoff chart. This one basically is your what you call maximum case scenario. It assumes you're operating at maximum weight. So any weight beneath that is going to shorten your takeoff roll. And then it assumes zero wind. So any headwind that you have is going to shorten your takeoff roll, like we talked about. Okay. So in this example, if I've got a, call it 7,000 foot density altitude, come over here, and what do we got here? This is 25 degrees of flaps. We'll assume 0 degrees of flaps. So I come over here, and I find out that for my ground run, I'm going to need at least 2,000 plus feet, maybe 2,200 feet. And then if I want to make it over a 50-foot obstacle, I'm going to need about 4,400 feet or so. This chart's helpful because it's already speaking my language. I don't have to do any calculations. I'm already being given I'm already basing it off my density altitude. Now, if that was pressure altitude, I would just have to do a math problem. But this is handy. So that's a less complex version. Either way, I know, hey, if I've got a headwind or I'm only loaded to 2,300 feet, then these values can kind of come down a bit. I don't know how much because the table doesn't tell me that, but I at least know what my limits are. All right. So that was takeoff. Let's talk a little bit about climb. You guys know when we talked about airspeed, the airspeed indicator, I defined the two V speeds, Vx and Vy. We'll go through a refresher on that in a minute. But that's what we're going to kind of centralize our discussion on here. But before we get to that, I want to define a couple physics terms. Are you guys familiar with the terms kinetic energy and potential energy?
Yes.
You are?
No.
Okay. Chris?
No.
Okay, good. So kinetic and potential energy are, from an extremely simple level, the two kinds of energies that an object can have. The object's either moving and it has kinetic energy, or it's at a certain altitude above the ground and it's got potential energy. If I've got a basketball sitting on the gym floor, just sitting still, it has zero kinetic energy and it's got zero potential energy. If I pick that basketball up and I hold it right in front of me and I hold it still, it's got zero kinetic energy because it's not moving, but it's got, let's say, 4 feet of potential energy. Why? Because if I let go of the ball, it's going to fall. And it's going to convert its potential energy into moving energy or kinetic energy. If I throw that basketball through the air at the hoop and I throw it up, it's going to have both moving energy and we'll call it altitude energy, potential energy. And if you look at the example I've got on the screen here, using this fancy roller coaster, if the roller coaster is sitting up here at A and it's not moving, then it's got potential energy, or if you want to say it's got the potential to fall because it's up here at a height of h. As soon as somebody applies a force to the roller coaster and it starts to move, it's going to convert some of that potential energy into kinetic energy because the roller coaster is going to start having a velocity. It's going to start to move. As soon as it comes through this dip here and goes back up to our final location, D, and let's just assume for simple purposes, there's enough friction in the system that it comes up to D and stops completely. As it goes up the hill, it's going to slow down, right?
Mm-hmm.
So you could argue that at that point, it's converting all of its kinetic energy, which is its motion energy, back into potential energy or energy, it's altitude energy.
Okay.
Is that pretty clear?
Yes.
Awesome. Okay. So based on that, the climb and really even the descent portion of your flying is going to be a trade-off between kinetic energy, potential energy, and the other kind of energy which the roller coaster didn't necessarily have, but the aircraft's engine, which is obviously providing thrust. Well, I guess our roller coaster did have a force applied to it. But the energies that you'll consider when you're talking climb and descent are kinetic, potential, and thrust. And as we've discussed before, thrust is one of the 4 fundamental forces of flight. It's a force. It's measured in terms of pounds, or if you're a metric type person, newtons. And there is a lot of, I'll say, confusion out there amongst pilots about thrust and power being the same thing, being different things. Truly, when it comes down to it, if you want to get technical, thrust and power are 2 different things. Thrust is a force, and power is a rate of transferring energy. The easiest way to think about that is your aircraft's engine uses fuel to combust and turn a crankshaft, which in turn rotates your propeller. So it is transferring mechanical energy from your engine into performing work. It's moving your aircraft by transferring mechanical energy into, in this case, kinetic energy or moving energy. So thrust and power are fundamentally 2 different things. You'll often hear them used in the same type definition, but it's not technically correct. They are 2 different definitions. And that's important because when we start talking about climb performance and Vx and Vy, which I'm going to redefine here in a second, you want to understand the difference between thrust and power because it does describe 2 different things. So as we finish our takeoff and we are now in a situation where we're going to climb to cruise altitude, there's 2 different ways that you can climb. And again, there's 2 that I'm going to define because it's kind of like the 2 different ideal states. But when you climb, you're either going to perform what's called a constant airspeed climb or a constant power climb. We'll go through each one of them here in detail. Your constant airspeed climb is just simply put, you're going to climb while holding a constant airspeed. If you're flying at 100 miles per hour and you decide to climb the aircraft, you're going to initiate that climb and your airspeed indicator is going to indicate 100 miles per hour the whole entire time. Now, in order to perform a constant airspeed climb, the aircraft's engine is going to have to work harder to convert its mechanical energy into kinetic energy. And the reason for that is if it didn't work harder to transfer energy like that, you wouldn't be able to hold a constant airspeed. Your airspeed would go down because you're fighting gravity. So in this example, we've got 130 horsepower, which is a unit of measure, a unit of power measure. And to hold our constant airspeed, your engine's going to actually have to output more horsepower. Its excess horsepower will be converted into potential energy. Make sense?
Yeah.
Yeah. Okay, good. Now, in the second scenario, where you've got a constant power climb, as we kind of alluded to earlier, in order to convert your current energy state into your new energy state or your increase in altitude, if you're not going to give the energy equation more power, then it's going to take energy out of somewhere. And that only thing it can do at that point is decrease your airspeed. So if I enter my climb at, say, 2,200 RPM, although my aircraft engine may have 400 or 500 more RPM to give until maximum power, and I pull back on the stick and climb at a constant power configuration, well, then the only energy that my aircraft can give up at that point is kinetic energy, which is airspeed, in order to reach our new altitude. So in this case, in the constant airspeed climb, horsepower is converted to potential energy. And in our constant power climb, because we're not giving the energy equation any more mechanical energy from the engine, you're going to have airspeed converted to potential energy. Good to go there? Does that make pretty good sense?
Mm-hmm. Yeah, sure does.
Okay. Now, this is important information because when you go to take your flight exam, and really if you want to become a safe and competent pilot, you're going to be performing either a constant airspeed or a constant power climb, depending on, what kind of flight configuration you're in, what altitude you're operating at. And so you'll quickly become familiar with, hey, I'm going to plan a constant power climb, so I will expect my airspeed to go down. Or I'm going to maintain an airspeed, but I'm going to have to give my aircraft engine more juice to maintain that airspeed. All part of getting to know your airplane that you're flying. Okay, so I'll say the second real important aspect of climb performance, as you're I'll say transitioning from takeoff performance, is what's known as best angle and best rate of climb. Did I reviewed this during the airspeed indicator discussion, didn't I? VX and VY?
Yes.
A little bit? Okay.
Along with some other speeds as well.
I don't expect you to remember exactly what it is unless one of you guys wants to go for it.
Ooh, I know one of them's like the maximum speed for a takeoff, and one of them's like the maximum altitude. Oh, it says it right there: max angle of climb, max rate of climb.
Yeah, no, it's good. No, you're pretty much almost there. They're both max altitude speeds. One of them allows you to achieve maximum altitude in a certain distance, and the other one allows you to reach maximum altitude in a certain time.
Got it. And
of course, even to this day, it's like if you get rusty, if you're a safe and competent pilot, and you get rusty on things like this, which we all do all the time, unless you keep up with it, your initial reaction is like, well, shoot, wouldn't those be like the same thing, like maximum altitude in a certain distance? Shouldn't that be the same thing as like maximum altitude in a certain speed? And the reality is they're not. They're completely different. And VX, which is the maximum angle of climb, which is the maximum altitude in a given distance, is, as you can see at this point, the altitude was much higher at this distance than VY, which is your maximum rate of climb, which is maximum altitude in a certain time. So where do we use these in practice? Here's my runway, and here's my airplane right here. And here's the end of the runway where you've got obstructions. And my runways, it's a small airport, so it's probably like 3,000 feet or some such thing. So in practice, the maximum angle of climb, VX, is used to ensure that you get above an obstruction in the shortest distance possible. We don't care about time in this case. We care about distance. Why? Because we know that the runway has a certain distance, and we know where the obstacles are. away from our starting point. So we want to climb at a speed for which we will gain the most altitude in a specific distance as possible.
But not necessarily the fastest time.
Exactly. Because at this point, we don't care about time. It could take us all day to get there. We just want to get there in the shortest distance.
Yeah, that makes sense.
When would you care about the max rate of time then?
Getting to optimal altitude as quickly as possible.
Yeah, that's exactly right. Because if you can get to your cruise altitude quickly, you will burn less gas getting there.
Okay.
Mm-hmm. And to be completely frank with you guys, when you're flying a single engine aircraft, it becomes somewhat of a rounding error to some extent. Once you start flying jets or heavy aircraft, I mean, you could, if it takes you 5 minutes longer to get to altitude, that could be like thousands of pounds of fuel. So very early on, when you start your training, you're taught to climb out at VX, clear your obstacle, and immediately, as soon as you're clear of your obstacle, get your aircraft to VY, to max rate, so that you can hit your cruise altitude as soon as possible. I probably have some words over here that can help me. Okay, so here's an example. Yeah. So assuming full power, VX will achieve 1,000 foot in 30 seconds, traveling 1 mile. Okay, so assuming this is 1 mile, it took me 30 seconds to get there, but I got to 1,000 feet. VY will achieve 1,500 feet in 30 seconds, but it takes longer. It takes 1.5 miles. So you can see in 30 seconds, which is a rate discussion, I climbed higher using VY, but it took me longer, which is why VX is used on your immediate takeoff planning. And then just one more quick note on thrust versus power, and I'm going to give a little kind of analogy. But VX depends on excess thrust, and VY depends on excess power. And it goes like this. This is the easiest way to kind of understand this. Imagine you're riding your bike up an extremely steep hill. In order to get to the top of that hill in the shortest distance, you're going to be pedaling that bike with as much force as you can, like out of the saddle type force. Whereas if you're trying to get there, maybe not necessarily in a short distance, but let's say you want to get there, to the same altitude in a given time, you're going to you may not be out of the saddle pushing with as much force as you quickly. In other words, trying to get the wheels to go as fast as they can. And so hence there enters that definition again. If you're pushing on the pedals as hard as you can, applying as much force as you can, going up a very steep hill, that's a force discussion. That's a thrust discussion. If you're trying to get to a certain altitude, but you're not necessarily concerned about doing it in like a really short distance, you're going to be pedaling as fast as you can, which is a power discussion. Why? Because the faster you pedal your bike, the quicker you are transferring mechanical energy into kinetic energy or moving energy. Does that make sense?
Yeah.
Yeah.
Okay. Yeah, so important from an airplane perspective, you're always going to climb out at VX. And once you clear your obstacles, you're gonna maintain VY to get you to your cruising altitude. And as you might imagine, the pilot's operating handbook is going to have a whole host of climb performance charts. This particular one, kind of going along the lines of our more sophisticated performance charts, is actually going to help you calculate climb distance, time to get there, and how much fuel you will burn up to your cruising altitude. Now this is pretty, this is pretty cool stuff, because if you're flying a complex aircraft that potentially burns a lot of gas, then your climb fuel burn rates can be very important to you, as is the time to get there and how far you'll fly. So this one works exactly like the last one. Given a certain set of conditions, you take your outside air temperature and you climb all the way up to your pressure altitude. So in this particular example, this individual is climbing from sea level up to 10,000 feet. And the chart's telling him that to climb from sea level to 10,000 feet, it's going to take let's see, 6 gallons of fuel. It'll take maybe 11 minutes to get there. And it's going to take 15 nautical miles to travel 11 minutes and burn 6 gallons of fuel.
That's really cool.
Yeah.
Yeah, pretty neat.
And this is applicable to each aircraft that we fly. So that will be in the aircraft?
In the manual, yeah. This will be in the aircraft manual.
Okay.
Go over here. I'm going to see. Oh, I think I've got, yeah, okay. I pulled out an example from the Aero. Now, so this one is not as complex. And what it requires you to do, it requires you to do math. So you take your density altitude. See, I'm at 7,000 feet maybe. I'm going to climb to 7,000 feet. And it tells me that I should expect, based on these conditions, a rate of climb of, give or take 500 and change feet per minute. Now, that's great, but, I have to do a bunch of math after that. At least this one here gives me my fuel burn, my time, my distance. I can find those values given this information, right? But I have to do a bunch of extra math. For instance, if I want to find my fuel burn, okay, I know that I'm going to be climbing at 500 feet a minute, so that's 1,000 feet every 2 minutes. I'm climbing up to 10,000 feet. So what's that, 20 minutes? And so I know that I burn X gallons per hour. So to get up to 10,000 feet, I've got to, you can find your fuel burn that way. If it's going to take me 20 minutes, then there's my time. And then my distance, well, in 20 minutes traveling at 100 miles per hour, because that's my VY, then I can give you what my distance is. So either way, either your aircraft handbook, Chris, to your point, is going to give you all this information published, or you're going to have to, or you're going to have to be like me and, okay, I know my rate of climb and I can find all that information if I so choose to calculate it.
Will we have to calculate it on the test?
Yeah. Mm-hmm.
Okay.
Yep. Now, lucky for us, the private pilot test, the written test, they give you the fancy charts, which is good.
So like on the instrument test, is that what you're saying?
No, so like for instance, if I took the Piper Arrow, which this chart comes from, if I took that to my flight test, the FAA examiner would expect me to use whatever material is in the operating handbook to plan the flight.
Got it. Okay.
Yeah. So yeah, written test, you get lucky. Flight test, if you're flying this particular aircraft, you just have to do some extra math. And don't quote me, but chances are, if you come prepared with a lot of this stuff pre-calculated, the examiner's not going to make you recalculate it, right? He'll check your answers, make sure everything looks good, and you'll rock and roll. But yeah, depending on what aircraft you're flying is what you'll have to demonstrate.
Okay.
Okay, so that's climb. After climb, we obviously cruise. And cruise Cruise is actually, you know, for your typical flight, you probably won't do a lot of performance calculations for cruise. It's a very predictable phase of flight. Altitude, of course, density, altitude is a factor. But you know, it's not as complex or dangerous, I'll say, as, you know, calculating takeoff distance, you know, making sure you're clear of obstacles, etc. So in cruise, of course, the big, you know, the big parameter that we're going to deal with is fuel. It's the point, or it's the phase of flight where most of your fuel is consumed. And so, depending on what kind of aircraft you fly and what charts are available, you'll be calculating, you know, range, how far can you go on your tank of gas, endurance, how long can you fly, based on a set of you know, assumptions, fuel burn per hour, total fuel consumption. I mean, all this stuff you can really calculate and become familiar with. To be honest with you, you know, fuel burn per hour is a number that you just memorize depending on what plane you fly. I mean, the Piper Arrow here that we look at a lot is 11 gallons per hour. The Beechcraft Bonanza, which is another plane that we fly, is 18 gallons per hour. It's just, you do so much flight planning that this metric right here, you commit it to memory.
And how much does the tank hold?
The Piper Arrow is a 50-gallon tank, 48, which is usable.
Okay.
The Bonanza is a 80 gallons, 74 usable. In the cruise performance tables, you'll also be able to calculate true airspeed. Of course, true airspeed is important because as you go up in altitude, as we've already learned in prior sessions, typically your true airspeed will increase. So you'll see as you go, as you study the tables that are associated with each of these items, you're going to be able to calculate fuel, true airspeed, and other parameters. So let's see. Oh, I think, yep, I do. And so here is a table that you'll find in a typical general aviation handbook, operating handbook. And they're tabular because it's what the manufacturer kind of expects the typical operating conditions to be. So on a standard day, which you guys happen to remember what standard atmosphere is?
29 or 92, 59 degrees?
Yeah. Yep.
0 degrees, mean sea level.
Mm-hmm. Yeah, and this is strange, right? Because this says 63 and 17. Interesting. Wow. Didn't notice that. That's interesting. Anyway, so you can calculate based on where you're going to fly, what kind of, you know, cruise operating conditions you can expect. Also, you'll get an idea of what the manufacturer recommends from a engine operation standpoint. So, you know, you're flying at 8,000 feet, and so long as you know, your ambient conditions are in the neighborhood, because, you know, as we said, standard atmosphere is kind of an ideal state, right? But you can expect to operate at these engine parameters, RPM and manifold pressure. You can expect you can expect this fuel flow in gallons per hour, and you can expect this true airspeed. And the manufacturer knows this because they've tested the aircraft at certain conditions, and they know that that's what it's capable of. So when you're planning your flight, and you say you're doing a long flight, you're flying from here to California, you know, the difference between planning 150 knots true airspeed and 161 happens to be pretty significant. So when you are planning your longer across countries, you utilize these tables to get, you know, down to the specific significant digit in accuracy. here is, I believe, that table just blown up. This particular format, you've got a couple different sections. You've got your standard atmosphere, and then you've got some assumptions for operation outside of standard atmosphere. So -20 below standard atmosphere and +20 Celsius above standard atmosphere. So this is the aircraft manufacturer kind of saying, hey, we know that it's not always going to be a standard atmosphere flight condition. So here's some tables, to give you some range, right? Depending on what the actual temperatures are. And so because of that, you have to actually get very good at it, at interpolating data. Because what if it's positive 14 degrees above standard? Well, it's not standard and it's not 20, so it's like somewhere in between, right? So if an examiner asks you, well, what's your fuel flow going to be? I guess that might be a bad example because it looks like it's the same. But if he asks you, what's your true airspeed going to be at +14 Celsius, 6,000 feet? Well, it's going to be somewhere between 158 and 161, and then you're going to have to calculate it. You guys get in your studies outside of aviation studies. Have you had to do interpolating of tables?
Yep.
Nope.
Nope. Okay, we're going to go through a quick example. Let's see. I got to look at the chart here to make sure I pick a good example. Yeah, we'll use true airspeed. So okay, we're going to plan a flight at 2,000 feet, and I'm going to say it's not going to be a standard day out, but we're gonna plan our flight at say positive 15, 16, 17. Actually, let's go in the opposite direction here. We're gonna plan our flight in a colder temperature. So standard day is going to be 15 degrees Celsius, and I've got -20 here. So I've got a 35 degree delta between the two tables. And for sake of argument, we'll try to pick something like halfway in the middle. So someone do some quick math. Is that 15, 0, 20? So it's like -3 degrees Celsius. So, and we'll pick, let's pick 6,000 feet. So if I've got a flight condition that is exactly halfway in between these two tables, then what I'm going to have to do is find the average, essentially the halfway point between any value in the table. So for instance, true airspeed, 158 in this table and 155 in this table. Since the temperature I'm picking is going to be halfway between the standard temperature and the -20 table, then I've got to find the halfway point between 158 and 155. Or in other words, I have to interpolate between the two values.
Oh, okay. I see what you're doing.
Mm-hmm. So what is that? 156 and a half, something like that.
Yep.
Yeah. Now this table doesn't really lend itself to a good example because you're thinking, well, shoot, that's like not a huge difference. But you'll find tables where fuel flow will differ by 2 to 3 gallons an hour, or true airspeed will actually be a lot different between two tables, and you'll have to interpolate like on a test. You'll have to say, all right, well, here's how you find the halfway point between those two values.
Okay.
And luckily, the really good thing is most of the test questions are exactly halfway. they don't challenge you to do anything other than try to find like the midway point. So let's see if I have a chart. Yeah, let me show real quick the Piper Arrows cruise chart, just to give you an idea of maybe a not such a complex example. So in this particular chart, Piper is basically giving you a graphical form of true airspeed versus wherever you're operating from a density altitude standpoint. And so if I know that I'm going to be flying at, say, a 6,000 foot density altitude at 75% rated power, which is a percentage of RPM, then I can come down here and it'll tell me I can expect to get about 164 miles per hour true airspeed. And then, of course, as you move down the power curve here, you get slower and slower. So yeah, so Piper in this specific aircraft, it doesn't give tables; it gives it in graphical, which is, it's okay. You can find your true airspeed, and I think I got one more here. And this particular aircraft also has a range chart. So given a density altitude, I can determine density altitude and power. I can determine how far I'll fly on a full tank of gas. So, and from here, Piper expects me to be able to calculate endurance on my own. If I know the range, then I can calculate my endurance. Endurance, if I forgot to define it, endurance is just how much time can you fly with a certain amount of fuel and a certain power setting. And range is how far can you fly on a certain power setting and a certain amount of fuel. And here's the handbook's example of range, similar to the arrows example. If you notice, this particular chart has two different sets of lines. One for a 45-minute fuel reserve and one for full tanks, meaning you will fall out of the sky, your engine will stop working at that point.
It's pretty impressive that the wheel fairings could create up to a 7% reduced distance.
Oh, wow. Jeez. That's nuts.
They have a lot of drag. I mean,
yeah. Oh, yeah. Yeah, the wheels for sure. So that's cruise charts. Usually, to be honest with you guys, power setting charts, or tables rather, power setting tables, and range and endurance graphs or charts are the most standard that you'll find. How far can I fly? How long can I fly? And in order to achieve that, what are my power settings based on certain ambient conditions? Oh, and how fast can I fly? What is my true airspeed going to be? Okay. Any questions on cruise?
no, sir.
Nothing?
No.
Okay. It's usually typically the least involved. You're just making sure you got enough fuel to get there. Okay, landing, similar to takeoff. It happens to be a pretty important sequence of your flight. And from a planning perspective, it happens to be takeoff's definitely more important because it happens to be the most dangerous statistically. but landing's like right there behind it. And similar to takeoff, we are concerned about landing distance, which just as a quick side note, typically, not always, typically landing distance is shorter than takeoff distance. So what can you guys tell me about that particular fact? What should that make you think about?
That landing distance is shorter than takeoff distance?
Yeah, what is that kind of, if you're kind of thinking about your cross country and traveling from A to B and then back to A where you came from, what is that specific physical phenomenon? What does that mean? What should that make you think about?
It doesn't matter how short your landing distance is. You need to consider your takeoff distance for where you're going, because you need to get back.
Yeah, if if you calculate your landing distance, and let's say you've got like a 2,000-foot runway, and your landing distance is 800 feet, and you're all excited because, hell, I can land there. Let's go. Well, you better do your takeoff calculation at that airport, because what if your takeoff distance is like 3,000 feet? Well, then you just landed somewhere for which you can't take off.
Oops.
Yeah, definitely have heard those sob stories. Again, when you're landing, wind is extremely important. Tailwinds can increase your landing distance by several percent. I'll have to look up the exact value, but I think it's like 5% for every 3 miles per hour of wind, which is pretty good, especially if you're dealing with very short runways. Weight, again, has a pretty sizable effect on your landing performance and your performance planning. Remember, from aerodynamics, the heavier you are, the higher speed is required to support the higher angle of attack and lift coefficient. Depending on where your aircraft is loaded, remember we talked weight and balance in the last class, is going to also affect how you're going to plan your landing performance. And once you get the aircraft on the ground, Newton's second law says that a heavier mass is going to take longer to decelerate, or it's going to take a higher force, one of the two. Okay. Density altitude comes into play again at landing. It's from a criticality standpoint, density altitude is a lot more important for takeoff. For landing, it's something that you notice. I think I gave the example during one of the last classes. One time I was landing at an airport in New Mexico, 7,000-foot density altitude, and right at the point that we were touching down, I had probably 50% of my throttle in, just to keep the true airspeed high enough to maintain lift all the way down to the touchdown point. Now, my indicated airspeed was the same for the same exact reasons we talked about in the previous slides on takeoff. Indicated airspeed is always going to be the same regardless of density altitude, but your true airspeed is going to have to increase to compensate for that reduced air density. So minimum landing distance will typically always be the value that you pay the most attention to. You always make sure that you've got enough takeoff distance to leave the airport that you're planning to land at. And similar to takeoff, performance calculations, landing is same deal really. Using ambient conditions, you can calculate both ground roll and total landing distance. We'll define those real quick while we're here. So let's just maybe walk through a quick example. So here's my gross weight, and for some reason this table only has one value, but gross weight is 1,600 pounds. Indicated airspeed at 60 miles per hour, regardless of density, altitude. It's always going to be the same. And the table is saying that your ground roll and your total landing distance is going to be different depending on where you're at from an atmospheric standpoint. So here's a sea level, 59 degrees Fahrenheit. That is standard. 25 and 50, 5,041, 7,532, all standard temperatures. And so what this is basically saying is, as I go up in altitude, based on the discussion we just had, I can expect to have longer landing distances because my true airspeed's got to be higher to maintain my lift all the way down to the touchdown point. And ground roll is the distance that your aircraft will travel after it touches the ground. So once you hit the pavement, that is based on all these assumptions. That is how far you'll travel before your aircraft stops. And total landing distance is assuming that you've got to land over 50-foot obstacles. That 1,075 is this distance all the way to stopping the aircraft. Whereas the 445 is the ground roll, assuming no obstacles, from the point you hit the pavement to when you stop. You can see that clearing obstacles really adds a lot of distance to your landing distance. Okay, all that good to go? Makes sense?
Yeah.
Okay. Yeah, always keep in mind this will definitely come up on the written test and come up during the exam, etc. True airspeed always increases as you go up in altitude. Indicated airspeed always stays the same, regardless of altitude. And here is the opposite of our takeoff chart. This is just the same thing, just landing, and it works the same way. Given your temperature and your pressure altitude at which you're operating at, as well as your weight and your wind and your potential obstacle, how far is my landing distance? So in this particular example, they're walking from a 15-degree standard day up to 4,000 foot. Their aircraft weighs, where are we at? Well, they're following the contour down to a specific weight down here, which appears to be 2,400 pounds. Then they're walking over here to the wind, and they've got a headwind of 6 knots. And over here to figure out how far they're going to take to stop the aircraft. You can see, just take note real quick, this is just kind of interesting, but you can see what the chart does with a tailwind, right?
Yeah, it actually increases the distance.
Yep. And the slope is a lot more aggressive for the tailwind than it is for the headwind.
Mm-hmm.
You see, the tailwind really, really affects how far it takes you to land. I don't think the takeoff chart had tailwind on it. It was just headwind. Okay, so that is landing planning. Again, just typically concerned with distance and ensuring at the end of the day that you've got enough distance to take off to. You can't forget that. Questions on landing?
Negative.
Okay. So with that, we've kind of completed the flight envelopes. takeoff, climb, cruise, landing. Just as a quick, 30-second summary, takeoff, we're, from a parameter perspective, we're concerned about distance. So we're calculating takeoff distance. We are interested if there's an obstacle. So we'll take that into account. During our climb, we are going to initiate our climb after takeoff at Vx to get to the highest altitude possible in the shortest distance, and then transition over to Vy once we have the obstacle cleared. Once we reach our cruising altitude, we've already done all our cruise planning, so we can expect our fuel flow to be a certain gallons per hour. We already know what our true airspeed is because we've consulted our tables. So we can effectively determine when we're going to actually get to our destination. And then our landing planning is similar to our takeoff planning. We're concerned about distance again and ensuring that we have got enough runway to stop, make a successful stop, and taxi off. So the one thing that we didn't really touch on during takeoff and landing planning, which is important and deserves discussion, is wind planning. You don't typically, at least I haven't done specific wind planning, because once you become extremely familiar with your aircraft, and I hate to put it this way, but a little bit of complacency sets in, and you know what your aircraft is published crosswind limits are, and you know what it's capable of, you'll be able to use your iPad or the tools that you typically use at your disposal and know right away whether or not you're able to fly the aircraft. With that said, let me pull up the Aero's operating handbook, and let's see if I can find the wind limits in this 300-page monstrosity. All right, weight and balance, emergency, flat, okay. Well, I don't want to waste our time trying to thumb through this, but there is a tiny section in here that basically says that the aircraft is certified to a certain crosswind limit. And maybe you guys have heard that before when we're talking about like commercial airliners, but your aircraft, based on its design limitations, will be able to only sustain safe flight with a certain crosswind component. And what this particular table here, this graph, does is calculates what the crosswind component is that you're dealing with based on the winds at your location. So let me draw something real quick here. Here's the runway. And let's say the wind is straight out of the east. This is north, by the way, at 10 knots. What is the crosswind for this particular scenario? $10 knots.
Sorry, I didn't realize that was a question. I apologize.
Oh no, you're good. You're good. The 10 knots, crosswind, straight crosswind, 10 knots. But you're never going to have a straight crosswind. Okay, you're going to have. Here's my runway. You're going to have your wind coming at an angle, and it's going to be 10 knots. But the way that your aircraft sees that from a crosswind perspective is the component of that wind that's hitting it from a perpendicular perspective. If you draw out, if we get into a little bit of physics here and you draw out force components, that 10 knot wind has a component in this direction, and it's got a component in this direction. And if you do, I don't know how good you guys are at doing trigonometry. I'm terrible at it. But if you do some trigonometry, you can figure out what this component is and what that component is, right?
Yeah, you need the angle and the distance.
Yeah. 90 degrees.
Well, that you have that one, but
Yeah.
I guess if it's 90 degrees, you have 45, 45.
Mm-hmm. Yeah. So long story short, you can figure these out. But why do that when you can use a graph like this? So essentially what this graph helps you do is figure out what this crosswind component is. Because that is what is published in your operating handbook. For the Piper Arrow, it is 13 knots. And so to save us the math, you essentially take your known wind value, which is these arcs right here, and intersect the angle at which the wind is approaching the runway at, and you can get your crosswind component, which is most important. And if you really care, you can get your headwind component. Crosswind component, which I circled, and headwind component, which is the down arrow. So quick example, I've got a runway of runway 36, which is straight north. And I've got a wind at 010 degrees at 20 knots. So I know, draw this out again. Here's my runway. My wind is at a 10-degree delta to the runway because I've got a 360 runway straight north and a 10-degree wind. So I've got a 10-degree difference between my wind and my runway. So I'm going to use this line on my chart, and I'm going to find my wind velocity of 20 knots. And the 10 degrees intersects the 20 knots right here. So I come down the chart and I find out that my crosswind component is probably about 5 knots. You can see intuitively as the angles get bigger, that crosswind component grows. So if it's a 20 knot crosswind at a 40-degree angle, which would be a wind direction of 040, I've got a little bit steeper crosswind component to deal with, probably like 11 or 12. Does that make sense to you guys?
Yes.
Mm-hmm.
Chris, yeah, and Alan, does that make sense to you?
Yeah, it does.
You don't sound convinced.
I need to spend a little bit more time with that chart.
Okay.
But I can do it offline. I think I understand. I'll go through some exercises later.
Yeah, just remember, there's a couple things you have to know. You have to know which runway you're using. And we haven't talked about this before, but the runway number is the direction that the runway points, magnetic.
Mm-hmm.
So, just for simplicity, runway 36 is a 360 radial runway. It points directly north. And so if you've got a wind that isn't directly head on, which would be 0 degrees, and say it's 20 degrees to the right, meaning it's hitting you at a 20-degree angle, or it's coming out of direction 020, then you just have to use this line here to intersect your wind velocity arc. Wind velocity, wind velocity, wind velocity. And then from there, travel straight down to the horizontal axis.
Yep, that's what I thought. Okay, cool.
Yep, you got it. Right on. Okay, we are doing really awesome on time. I've got a video that I want to watch. Before we do that, though, any questions you guys wrote down on the material? Anything crazy? Just needs re-explained? Difficult? I didn't do a good job explaining anything.
No, actually, this was pretty good. Pretty helpful, and all the charts are really interesting. Lots of planning. I'm looking forward to figuring out where you start, because there's no way you can remember everything about your flight plan while you're making it. I got to think that there's some place you ultimately end up writing it, and you can use it for reference as you're flying. But
yeah, The cool thing is you got a bunch of like iPad tools that'll do everything for you. You know, it's like you can totally forget how to do this kind of planning, but you never know when someone's going to ask you to do it for them. You know.
Yeah.
Or when your iPad's going to lose batteries.
You know what? Amen. Because I mean, there's only only a few people have like a ton of iPads and iPhones. I mean, I know people that do carry a backup iPad in the cockpit, which is a safe thing to do. And I know people that also carry paper charts because they're afraid their iPad's going to blow up and won't work. But yeah, no, you're totally right. You can't rely on it if it fails. So, all right, let's copy this and send it to you guys. Now, just a quick disclaimer. This is a shorter video. It's not one of the accident videos, thank God. But it's a live dash camera from an airplane that takes off from a short runway. I'm showing this just to kind of do some correlations between what we talked about in real life. I don't think I really do not endorse what this individual did. I think it's kind of, I mean, hopefully you guys think the same thing after you watch this. I think it's pretty stupid. But this person did a takeoff distance calculation and realized that he had just enough distance to take off over an obstacle. I don't know what the number was. I didn't look it up, but it had to be within feet because you guys just watch this. It's nuts. So
Okay.
I don't endorse it, but
This is not what to do on our first flight lesson.
yeah, you don't. Yeah, I mean, I was like biting my finger off watching this thing. So when you guys are finished, just go off mute, and then we'll come back and talk about it. Okay?
Okay.
See ya.
Wow.
Is that nuts or what?
Dude. I mean, I get what you're saying. Like, I don't applaud his risk taking there, but I do like that he managed to let you just fly the aircraft and not overreact, not try and pull up and get additional altitude and stall the plane.
Oh yeah, I mean that kind of It's funny you mentioned that actually. That it kind of brings back some topics from aerodynamics, right? The more you increase angle of attack, the less airspeed, so you're not going to be able to, not as much lift. So that's nuts, isn't it? When I watched it, I was like, holy shit.
Yeah, I mean, wow, that was crazy.
Yeah, and let's see if Chris, did you finish? Is the video over for you yet?
If she's watching all the way to the end, it's probably not. I didn't listen to the whole closeout.
Oh, okay, gotcha.
He was just yakking about footage he puts together and stuff like that.
Yeah. I mean, he makes a couple interesting points there that I didn't mention during the session. You know, the performance charts are for a new airplane. So typically the airplanes we fly are like decades old, right? They're in good shape, but they're old.
Yeah.
And I mean, they're just not going to perform in the same exact manner as a brand new aircraft. And you know, you don't want to test the safety factor of a performance chart, right? You want to add your own minimum to whatever you feel is safe and whatnot. So,
That's nuts.
yeah, was that crazy or what?
He just had a baby.
No, he wasn't.
Leave his wife and children. Huh?
No, he wasn't the guy who had the baby. Wasn't the pilot. The guy who had the baby was the guy annotating the film.
Oh.
He made a comment. I don't know how I missed this, but this little guy was a distraction. So he had missed the video when it went viral.
Oh, okay. Okay.
I thought it was the pilot blaming the fact that he
Well, I'm pretty sure. Yeah, no, that's not how I interpreted it.
Oh, funny.
Yeah, you guys see the quick bullet they put up there about density altitude? I don't think they said how high, but you can see some mountains, so you know it's thin air. So yeah, that's nuts. That just goes to show. I mean, he did his calculation, and it turned out to be, correct, I guess. But I don't know. You always want to add. That guy said 50%. That might be a little. That might be a little much, but you definitely want to add a little safety factor to make yourself sleep at night.
Yes.
And basically everything you do in flying. So anyway, I thought that was a pretty good visual of what can happen when you kind of plan exactly to the numbers and what it's going to look like. So anyway, so that's the material. What anything at all that wasn't clear, or you want more explanation, or hell, even stuff from the prior sessions you guys want to talk on?
No, I'm good. I'm really looking forward to the map sections. I'm sure we're going to get to at some point.
Mm-hmm.
But so far, I think I'm good.
Okay. Chris, you good?
Yeah, I'm good. I actually have to jump to dinner. So
okay.
Thank you so much.
Real quick before you go, Chris, what you're out for the next class because you're going to Europe for a little while, right?
No, I'll be in the class. Yeah.
You're planning on doing it? What? I didn't know if it's too late for you.
No, I'd rather do it. It's kind of awkward timing, but it works. I'd rather wake up really early and do that and then get going. So
okay, hey, heck yeah, I love it. All right, sounds good, guys. I'll put a quiz out and then just let me know what questions you have.
Cool. Thanks, man.
All right, see you guys.
Yep. Bye, dude.